Good morning, students. Now I am going to start the class. We are discussing the semiconductor chapter, right? And students, is it clear my voice? The board also appearing clearly, na? Yes or no? Yes, if you have any query, you write in the chat box. I am going to start the class. Okay, students. And now the thing is that we are discussing the semiconductors chapter, right? What is our chapter name? Semiconductors. What is a semiconductor and what is its use? Okay, semiconductor means, let us go for it. What is the definition of the semiconductor? Semiconductor, we know that whose properties lies between the conductors and insulators. And the semiconductors are classified into two types, right? Okay, semiconductors are the materials whose properties lies between conductors and insulators. Conductors and insulators. This is about semiconductors. Example for the semiconductors is, okay. Example for the semiconductors. Elementary semiconductors example is, elementary or the example is germanium and silicon. And compound, if you take the compound semiconductor, gallium arsenic is an example, and cadmium sulfur is an example. Okay, this is about semiconductors. And semiconductors basically classified into two types. Okay, right. Now, semiconductors are two types. Semiconductors are two types. Okay, semiconductors are two types. The first one is the what? Intrinsic semiconductor. Second one is the extrinsic semiconductor. Intrinsic semiconductor, and the next one is the extrinsic semiconductor. These are the two types of semiconductors. There are various applications in the various fields are there for the semiconductors, right? In the televisions, okay, the television size now LED TV we will tell. LED means, LED means, okay, LED means light emitting diode. It is made with the semiconductor, right? And so many components we will make with the semiconductors that we are using the computers and electronics, okay, right, and robotics and some others. And what are the intrinsic semiconductor? Students, is my voice clear? Is my voice clear? Writing also clear na? Very good, Sitamani, Aditi. Okay, thank you. And I am continuing. Now, first one is the intrinsic semiconductor. What is an intrinsic semiconductor? Which is said to be intrinsic semiconductor? Intrinsic semiconductor means it is the pure form of semiconductor. Pure form of semiconductor is called as intrinsic semiconductor. Okay, pure form of semiconductor means without any impurities. Pure form of semiconductor. Pure form of semiconductor is called as intrinsic semiconductor. Okay, intrinsic means pure form. Pure form means no impurities, right? Intrinsic semiconductor, pure. Then how many types of intrinsic semiconductors are there? What are the example for the intrinsic semiconductor? The example for the intrinsic semiconductor. Okay, example for the intrinsic semiconductor is germanium and silicon. Germanium and silicon are the example for the intrinsic semiconductor. What is intrinsic semiconductor? What are the characteristics of intrinsic semiconductor? Intrinsic semiconductor, if you will take the germanium or silicon, the germanium and silicon both are the tetravalent. Okay, that means four valency electrons are present for each germanium. For example, if you take the germanium sample, it has many germanium atoms, right? It has many germanium atoms like this: germanium, 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 germanium. But each germanium atom has the four valency electrons. Each germanium atom has four valency electrons like this. If you have any query, you can ask me. Okay, it is very interesting actually, the semiconductors chapter, and it was very easy also. This is a germanium. It has the four valence electrons. You see here around the germanium, every germanium I am writing the four dots. These dots indicates that four valency electrons, right, for every germanium, and then they will form the covalent bonds by sharing the electrons. Valency electrons, tetravalent means valency electrons are the four, and every germanium, right, every germanium has four valency electrons. These four valency electrons forms the four covalent bonds with the neighboring germanium atoms. Look at here, it was very interesting. This is the germanium. This germanium has four valence electrons. One, two, three, four. These four valence electrons forms the four covalent bonds with the neighboring germanium atoms. And at that moment, what happens? This, if you take the middle germanium, you see here cursor, you can follow. This middle germanium has the four valency electrons, four dots I kept, and then this dot indicates the what? The dot indicates electron. Okay, dot indicates electron. Dot indicates electron. Four valency electrons forms the four covalent bonds with the neighboring germanium atom. This is one, two, three, four. Four covalent bonds forms. Like this, here all the germaniums are in bond. But the covalent bonds are the weak bonds, but even at room temperature also, some of the covalent bonds will be breaks. When one covalent bond breaks, then what happens? When one covalent bond breaks, this electron will be escaped from the valency shell, okay, valency orbit. When the electron escape from this here vacancy is created for the bond. This vacancy is called as the, this dot is called as electron, and the vacancy is represented with the small circle, that is called as hole. That is called as hole. Okay, that means actually initially these so many electrons are there, but these all electrons are in the orbit, in outermost orbit, valency orbit. They are in the bond with the neighboring atoms. Firstly, what happening here, one of the electron which is in the valency orbit, okay, if it escapes from the bond, at that moment what happens, one free electron is generated. This is called as the free electron. This is called as the free electron. Okay, and along with the free electron, one vacancy is created for the bond. That vacancy is called as the hole. That vacancy is called as hole. Understood? Is it appearing, students, clearly or not? If any color is not appearing clearly, you tell me, I will not use that color. Everything is clear now? Right. And now I will explain this one once again. And now this is the valency band. You know about the valency band, right? This is the valency band. Okay. This is the valency band. And this is the conduction band. This is the conduction band. Okay. You know energy bands in the last class we discussed. In the valency band, valency electrons are there. Okay. The valency electrons are there. And here electrons are there. Okay. And when the valency electron, when the energy band means what? Energy band means it is a group of energy levels. Group of energy levels. When the electron jumps from valency band to conduction band, right? Okay, by gaining the energy, then it will escape from the band. Here vacancy is created. This vacancy is called as a free electron. Okay, and the vacancy is created in the valency band, that is called as the hole, right? How many bonds breaks, how many covalent bonds breaks, that many free electrons and that many holes will be generated. For example, one more covalent bond break it here, then this electron will be escape from here. When the electron escape from there, what happens here? One free electron is generated, one free electron is generated. Along with that, here one vacancy is created, that means a one hole. How many covalent bonds breaks, that many free electrons and the holes are generated. For example, one more electron jumps from valency band to conduction band, that means the bond breaks, then one more free electron is generated, then here one more vacancy is created, right? Like this, how many free electrons are generated, that many holes are generated. That means in intrinsic semiconductor, the number of holes equal to the number of electrons. How many free electrons generated, that many holes generated. But actually what happens, due to the holes also current will be flows in intrinsic semiconductor. You see here, for example, here the hole is there. What is the meaning of hole? Vacancy for electron is called as the hole. The vacancy is created at here. That vacancy is filled with the neighboring electron. For example, the electron from here jumps to here, and at that moment, what happens? The whole here vacancy will be created, right? That means vacancy. Actually, what happened? This electron goes to here. This vacancy is filled. Then here vacancy is created. That means hole will come to here. Indirectly, the electron moves from here to here, but the hole will become from here to here. Right? That means we say that the electrons are holes also moves. Holes also moves. Really, the holes not moves, but due to the motion of the electrons in the valency band. For example, this here the vacancy is created. This vacancy is filled with this electron. Right here vacancy is created, and this vacancy is filled with this electron. Then here this electron goes to here and fills the vacancy. Then here vacancy is created. Indirectly the vacancy is initially at here, it goes to here, next here, like this. The hole is will be travel in the valency band and electrons will be travel in the conduction band. This is about intrinsic semiconductor, right? Is it clear, students, till now? Okay, I will not use that color next time. Next continuation. I am going to erase you. If you want, you take the screenshot. Okay, next one is the some points related to this I am going to give. That what are the points related to the intrinsic semiconductor? In intrinsic semiconductor, what happening? Tell me. Number of electrons equal to number of holes. Is it right? In intrinsic semiconductor, number of electrons equal to the number of holes. In intrinsic semiconductor, in intrinsic semiconductor, number of free electrons equal to the number of free electrons equal to the number of free electrons equal to the number of holes, right now? Okay. What is the meaning of hole? Hole means what? Hole is the Okay, vacancy for electron, right? Vacancy for electron. Where the holes forms in the valency band. Okay, holes forms in valency band. Okay, holes forms in valency band. Why? When electron escape from valency band to conduction band, okay, then vacancy is created in the valency band. That vacancy is called as in hole. Okay, and next one is the, we are telling that the electron density equal to the hole density, that is equal to called as intrinsic charge carrier density. This Ne is called as electron density or electron concentration. Electron density means number of electrons per unit volume. Number of electrons per unit volume. Number of electrons per unit volume. And nh means, hole density. Hole density means number of, hole density means number of holes per unit volume, but actually the electrons and holes are same number in the intrinsic semiconductor, right? Okay, now next one is the Ni. Ni is what? This is called as intrinsic charge carrier density. What it is said to be? Intrinsic charge carrier density. Intrinsic charge carrier density. What is the meaning of intrinsic charge carrier density? Intrinsic charge carrier density means, intrinsic means pure. In the pure charge carrier density, other electron density or hole density in the intrinsic semiconductor is called as intrinsic charge carrier density. In that is, this is Ni equal to Nh equal to Ni. It is for only intrinsic semiconductor. In intrinsic, how many electrons are generated, that many holes are generated. Is it right? Have you understood? Is it clear? Students, is it interesting? Right. And the next one is the, I am going to explain current in intrinsic semiconductor. Current in intrinsic semiconductor. How to find out the current in intrinsic semiconductor? Current in intrinsic semiconductor. Very interesting actually topic. I like this topic in the physics. Semiconductors I like. Okay, right. Now, what is the current in intrinsic semiconductor? What are the charge carriers in the semiconductor? In the semiconductors, not only electrons, holes also charge carriers. Have you understood this? In intrinsic semiconductor, not only electrons, holes also charge carriers. Is it correct? Current in intrinsic semiconductor. We are discussing about the intrinsic semiconductor, right? Now, current in intrinsic semiconductor. Why the current will be generated? Okay, current in intrinsic semiconductor is due to the electrons and holes. Current in intrinsic semiconductor. Actually, electrons in the moves in the conduction band, holes moves in the valency band. Due to that, both provides the current. That means current in intrinsic semiconductor is is due to electrons and holes, right? That means holes also charge carriers. Holes also charge carriers. Right? Current in intrinsic semiconductor is due to electrons and holes. That means here electrons and holes are the charge carriers in the semiconductor. Electrons and holes are the charge carriers. Holes are charge carriers. Electrons we can take as negative charge, and holes we can take as related to electrons. Holes we can take as positive charge. Okay, holes are charge carriers. They can carry the charge and they can provide the current. Then the current in semiconductor is the electron current is hole current. Then electron current is what? Electron current we write is current formula in terms of drift velocity. If you write NEAVD, we have to write. You know this formula. That is electron current we write is NEA. Electron drift velocity we have to take, and this is IH means whole current. Whole current. Whole current we write as NEAVH. We have to write. Then we will get as, we can common the NEA here, then at that moment we will get as NEA of VE plus VH. This is the formula for the what? It is the formula for the current in semiconductor. Current in semiconductor. We write the terms which are present in this. What is N? Okay. Intrinsic charge carrier density. Charge carrier density means number of electrons per unit volume or the number of holes per unit volume. It is a we can write it as a number density also. Number density. Number density. Number density of electrons. Number density of electrons or holes. How many electrons are there per unit volume? How many holes are there per unit volume? That is called as small n. E is the electron charge. A is the area of cross section. Okay. A is the area of cross section, and you take the screenshot and note it. Okay. Very interesting topic. Okay. Very, very interesting topic. This chapter, and it is belongs to electronics. Okay, when you will go for the BTech electronics and communication, you will learn totally this only. Okay, and in my post graduation also, this is my specialization, right? In specialization, you in physics also some branch you, if you like that you can select. Okay, right. I like this electronics, that's why I took it. And E is what? Electron charge. E is what? Electron charge. And what is the VE? VE is the drift velocity of electron. Drift velocity of electron. Drift velocity of electron. And VH is the drift velocity of hole. Drift velocity of hole. Okay, right. A is what here? A is the area of cross section. These are the terms which are present in the current formula. This is the current in intrinsic semiconductor. Now let us continue. Right? The current in intrinsic semiconductor. Are you getting, students? Everything, Priyamato and others. Is it clear, students? Okay, let us start. Now, at temperature 0 Kelvin, at 0 Kelvin, semiconductor will act as a insulator. Okay, at 0 Kelvin, semiconductor act as insulator. Why at 0 Kelvin semiconductor act as zero insulator? Can anyone write in chat box? At 0 Kelvin semiconductor act as insulator. Semiconductor act as insulator. Why? I want the reason. Okay, why? Write in the chat box. Okay, what is the reason? Can you explain in one word? Okay. Actually, at 0 Kelvin, what happens? There is no energy to break the covalent bonds. Is it right? Then that means all the covalent bonds are fulfilled. Then no electron to jump into the conduction band. Actually, to jump into the conduction band, to escape from the band, okay, electron require energy. But at 0 Kelvin, the thermal energy becomes zero. No energy. That's why here, the what happens it here at 0 Kelvin? At 0 Kelvin, what happens? At 0 Kelvin, all the valence electrons tightly bound to the nucleus. Free electrons are not available. That's why at 0 Kelvin, conduction band is empty, right? Free electrons not available. Conduction band is empty. Okay, free electrons are not available. Free electrons are not available. Why not available? Because at 0 Kelvin thermal energy is 0. It cannot gain any energy to jump into the conduction band. That's why conduction band is empty. When conduction band is empty, then the free electrons are not available. Then when free electrons are not there, holes also not there. Is it right? Free electrons are not available. Hence it acts as insulator, right? Hence it acts as insulator. Insulator. Got it? You see here, this is the valency band and this is the conduction band. For example, here we are taking that are the few electrons are in the valency band. These are the electrons in the valency band, and now no electron jump to the conduction band. At that moment, the conduction band is empty. Right? The conduction band is empty. CB means conduction band. Conduction band is empty means free electrons are not there. If electrons are not there, then holes are not there. No electron, no hole means no current. Got it, students? At this temperature, electrons are not able to move. Not able to move. It is not able to move means actually electron availability is only not there. At 0 Kelvin, free electron availability is not there. If availability is there, then whether they are going or not, it is not. It is a matter. There is no availability of free electrons. That's why there is no current. Okay, even holes also not there. And can anyone write? No, Puneet said that energy difference between the covalent band and valency band is more. That is more in the insulator, but semiconductor it is less only. But what happened, actually energy gap is less even though to jump some of the energy required that will come from thermal heat at room temperature. But at 0 Kelvin, right? 0 Kelvin means minus 273 degrees Celsius. No temperature, no heat, no electrons jump to the uh, conduction band. That means electron will not free to move. That only free electrons can constitute the current, can produce the current. In rubber also electrons are there, but the free electrons are not there. That's why current will not flow. Right? Okay, students understood now? Okay, very interesting. Okay, keep listening and enjoying the subject. And if you want advanced technology, you should learn this semiconductors. Right? Now I'm going to continue. I'm going to erase this. Right. Now at room temperature, what happens if temperature is greater than 0 Kelvin, right? If temperature is greater than 0 Kelvin, okay, then the R at room temperature, what happens at room temperature? At room temperature, some of the electrons jumps from some of the electrons some of the electrons jumps from where? Actually at room temperature also some of the thermal energy is there. Then some of the electrons jumps from where to where? Valency band to valency band to the conduction band. Valency band to the conduction band. That's where some of the free electrons will be produces, right? Due to that, some of the holes also generated, right? Some of the electrons jumps from valency band to conduction band by gaining thermal energy. By gaining thermal energy, that's why it acts as conductor. Okay, hence it acts as conductor. hence it act as conductor. Okay, that means semiconductor will act as a insulator at 0 Kelvin, but it act as a conductor at a room temperature or more than room temperature. Okay, right. And now next, what is a extrinsic semiconductor, or what is the Fermi energy level? One more important definition I am going to explain. That is the Fermi energy level. What is Fermi energy level? Fermi energy level. Okay, Fermi energy level. Fermi energy level means average energy level. Average energy level. Again, the board is not responding. Wait for a few seconds. Stay in class. Today I will continue up to 2 o'clock. Right, let us start. Okay. Now, if temperature is greater than 0 Kelvin, what happening at here? Some of the electron jumps from valency band to the conduction band. Due to that, what happening? It act as conductor. Some of the free electrons available, some of the holes are available. That's why it act as conductor. Next topic is the what is the Fermi energy level? Fermi energy level. Fermi energy level. What is a Fermi energy level? What is the definition for this? Fermi energy level means it is the average energy level occupied by the average energy level occupied by the free electrons which are present in the average energy level. I will explain. Don't worry. Average energy level. Average energy of electrons in average energy of electrons in valency band. In valency band. Average energy of electrons in valency band and holes in holes in sorry, electrons are present in the conduction band, na? Average energy of electrons in the conduction band and holes in the valency band. Generally, now holes are present in the valency band. Okay, I will explain with the diagram. Fermi energy level is the energy of electrons in conduction band plus energy of holes in valency band by 2. This average energy is called as this average energy level, that is called as the Fermi energy level. Okay, Fermi energy level. Next, what is the location of the Fermi energy level? That is important. Okay, I will explain this one very carefully. You have to hear. Okay, and it was very easy. And now this is the what happened? See here, this is the valency band. Okay, and this is the conduction band. This is the conduction band. Now, in the valency band, free electrons are there. What are there? No, 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 no. Free electrons not. Generally, the electrons which are in the bond, they are there. And when these electrons will jump to the conduction band, then what happens? Here, the electron jump to here. Then at that moment, the vacancy is created. The vacancy is created in the valency band, that is a hole, and here electron will goes. And similarly, like this, when electron jumps to the conduction band, then the vacancies are created in the valency band. These vacancies, small circles, are called as what? What they are called? These small circles are called as the holes. But how many electrons are present? How many free electrons present? That these are what? Free electrons. Why they are called free electrons? They escaped from valency level. Outermost orbit of atom, they escaped. That means they are free from nucleus attraction. That's why the electrons which are present in the valency band are free. That's why they are called as the free electrons. And the vacancies are created in the conduction band. Sorry, vacancies are created in the valency band for the electron. These vacancies are called as holes. Okay, right. Then how in the intrinsic semiconductor, how many electrons, free electrons forms, that many holes are forms. And then here you see here, these electrons have the some energy, right? This electrons energy, for example EE, and these holes also have some energy, that then that is EH. Their average, but they have the equal energies, that's why their average will be at the middle, right? This is the Fermi energy level. The Fermi energy level is at the middle of the, at the center of the valency band and conduction band. If you find out the average of these two energy levels, this energy plus this energy, if you will do the average, you will get the middle. For example, this one has the 2 electron holes. For example, holes have the 2 electron holes. This one have the 4 electron holes. Their average is 3. 2 plus 4 by 2. 3. 3 is in the middle, right? Okay. That means Fermi energy level. Fermi energy level is the average energy level. Average of energy of electrons and energy of holes. Okay, average energy of electrons in conduction band and holes in the valency band is called the Fermi energy level. The Fermi energy level in intrinsic semiconductor, what is the location? What is the location? Okay, just they one time for the one mark question they asked the um, Fermi energy level location in the intrinsic and extrinsic semiconductors also. Fermi energy level is Fermi energy level is at the middle of, right, valency band and conduction band, right, at the midpoint, at the center, at the center of, at the center of valency band and conduction band. This is in intrinsic semiconductor. We are all till now we are discussing about intrinsic semiconductors only. The semiconductors are two types. One is intrinsic semiconductor and other one is what? Other one is what? Do you know? Can anyone write what is the name of the other one? Write in the chat box, students. What is the name of the other one? What is the name of the other one? Okay, let us go for the other one. And that is extrinsic semiconductor. Anybody typed? Right, good Aditi. Extrinsic semiconductor. Right? Extrinsic semiconductor. What is an extrinsic semiconductor? What is an extrinsic semiconductor? Intrinsic means what? What is the definition of intrinsic semiconductor? Write in the chat box. What is the definition of intrinsic semiconductor? Which is said to be intrinsic semiconductor? Second one we are discussing now, that is extrinsic semiconductor. Okay. First one we already completed the intrinsic semiconductor. What is extrinsic semiconductor and what is intrinsic semiconductor? Already we completed the intrinsic. Can you tell what is intrinsic? Which semiconductor is said to be intrinsic semiconductor? Extrinsic semiconductor means it is the impure form of semiconductor. Pure form is called as intrinsic, right? Impure form of semiconductor. Impure form of semiconductor is called as impure form of semiconductor is called as extrinsic semiconductor. Is called as extrinsic semiconductor. Extrinsic semiconductor. Okay, what is extrinsic semiconductor? Impure form. That means some impurities you should add. Impurities you should add. Process of adding impurities is called as doping. What is a doping? Doping means what? You know that, for example, if you want to increase the performance of some athlete, okay, right? At the moment that they, for example, some players, they will go for the dope test, right? In the doping test, some members will uh, catch. At the moment, they are not allowed to play in the exams, and if they will get any medals, then they have to get back. They have to give back. Why? Why? What is the need? Because without doping, they have to play. And in the doping, what happens? Doping means they will take the some medicines and uh, some materials, some foods which increases their energy. Similarly, intrinsic semiconductor is the pure form of semiconductor. In that, some current will be generated. To increase the amount of current in the semiconductor, we have to add some impurities. We have to add some impurities. That the process of adding impurities to a pure semiconductor is called as doping, right? The process of adding the process of adding impurities the process of adding impurities to the pure semiconductor. The process of adding impurities to the pure semiconductor is called as what? Is called as doping. What is doping? Doping means adding impurities. Adding impurities. For example, how you can generate the extrinsic semiconductor, right? Extrinsic semiconductor is very simple, right? For example, added to the if some impurities added to the pure semiconductor. What is a pure semiconductor? Pure semiconductor is nothing but intrinsic now. Is it right? Pure semiconductor is nothing but intrinsic semiconductor. Is it right? Intrinsic. If impurities added to the pure semiconductor, then we will get the extrinsic semiconductor. Is it right? Got it? Extrinsic semiconductor. Then next, extrinsic semiconductors are two types. That is based on the doping. You may add the different types of impurities based on the impurities. Extrinsic semiconductors are two types. Based on impurities. based on impurities. Extrinsic semiconductors. Extrinsic semiconductors classified into classified into two types. Classified into two types. Very easy chapter and very interesting chapter. Okay, that are first one. A. A is the A is the P-type semiconductor. What is that? P-type semiconductor. P-type semiconductor. And other one, B is the N-type semiconductor. N-type semiconductor. Okay, semiconductors are two types. Extrinsic semiconductors. Okay, right? Semiconductors are classified into two types: intrinsic and extrinsic. In that intrinsic semiconductor, only one type, but extrinsic are again two types. There are the p-type and n-type semiconductor. Now we will discuss about the p-type semiconductor, right? How it is? So many members are missing. Very interesting and easy topic. P-type semiconductor. Which is said to be p-type semiconductor, and what type of doping we have to add based on the doping, based on doping impurities. Impurities means doping only. Okay, based on doping material, right? Based on doping material, extrinsic semiconductors are classified into two types, right? What is a p-type semiconductor and how we can make the p-type semiconductor? Students, do you have interest? Right. What is a p-type semiconductor? P-type semiconductor means if trivalent impurities. What? Trivalent impurities. If trivalent impurities are added to, if trivalent impurities are added to pure semiconductor, if trivalent impurities are added to pure semiconductor, if trivalent impurities are added to the pure semiconductor, then it is called as, then it is called as p-type semiconductor. P-type semiconductor. What is a p-type semiconductor? How we can make the p-type semiconductor? P-type semiconductor means you should add the trivalent impurities. Okay. For what we have to add the trivalent impurities? For what we have to add the trivalent impurities? For the pure semiconductor. What are the example for the pure semiconductor? Can you give example for the pure semiconductor? What are the pure semiconductors? Write in the chat box. What are the pure semiconductors? Trivalent impurities. Can you give the example of trivalent impurities? Can you give the example of trivalent impurities? Example of trivalent impurities. Okay, trivalent impurities. Trivalent impurities example. Okay, trivalent means three valency electrons should be there. Then for that example is boron, aluminium, gallium, indium, thallium. These are all example for the trivalent impurities. Trivalent means what? How many valence electrons it should contains? It should contain three valence electrons. In the outermost shell, outermost orbit, it should have three valence electrons. Right? And now I will tell very simple. And if trivalent impurities, trivalent impurities, for example, I am taking the trivalent impurity as okay, trivalent impurity is boron. If this is added to the pure semiconductor, okay, pure semiconductor. What is the pure semiconductor? What is the example of pure semiconductor? Can you write what is the example of pure semiconductor? Germanium or silicon. Germanium or silicon. Then what you will get? Then what you will get? Then you will get the p-type semiconductor. How you will get the p-type semiconductor? If trivalent impurity is added to the pure semiconductor, then that is called as the p-type semiconductor. P-type is extrinsic or intrinsic semiconductor? Whether p-type is an extrinsic or intrinsic semiconductor? Whether p-type is extrinsic or intrinsic semiconductor? Whether p-type is extrinsic or intrinsic semiconductor? This is my question. Write in the chat box. Now, let us discuss about its some properties and how it will works. Okay, right. Listen very carefully. And for example, one boron atom, we are adding to the pure germanium. Okay, I am adding to the pure germanium. Germanium is a tetravalent. Means four valency electrons are present in the germanium. How many valency electrons? Four valency electrons. Four, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right? The four valency electrons are present for the germanium and one boron atom I am adding for the germanium sample. Okay, germanium is a pure. For the pure, I am adding the impurity. Impurity is the boron. Boron is what? Trivalent. When trivalent impurities are added, then what happens? This trivalent impurity boron has three valence electrons. These three valence electrons forms the three covalent bonds with the neighboring germanium atoms. How many covalent bonds? Three covalent bonds with the neighboring germanium atom. But there is a one vacancy is there. One vacancy is there for the bond. The fourth bond, boron has three valence electrons, three covalent bonds formed at here. One, two, three. But the fourth bond is incomplete. Fourth band is incomplete. To complete the fourth band, there should be one electron required. That means there is a vacancy is created for the electron. This vacancy is called as the hole. This vacancy and these valence electrons are all the electrons which are drawn in this diagram and they are present in the valency band because these are all valency electrons. Okay, and now we will draw the energy bands and this is the valency band. This is the valency band and this is the conduction band. This is the conduction band. And now what happens? The energy gap between the valency band and conduction band is called as forbidden energy gap. Forbidden energy gap. Now let us see here. In the one boron atom created the one hole. Have you understood this? One boron atom created the one hole. But like this, we will add so many boron atoms. So many boron atoms we will add, and due to that so many holes are generated. So many holes are generated. For example, this is generated due to the boron atom impurity. Like this, for example, 10,000 boron atoms you added. 10,000 boron atoms you added means 10,000 holes are generated. And along with that, some of the covalent bonds breaks. For example, electron escape from the valency band to conduction band. Then when due to that what happens? Electron generated here, vacancy is created. How this one is formed? This pair of electron and hole due to the break of covalent band. For example, from this here one electron goes to here free. Okay, at the moment here vacancy is created. That vacancy is called as the hole. During that electron is generated and hole is generated. Like this, due to the impurity of boron atom, the holes are generated in the valency band and the more holes will be generated because of the more impurities. But some of the covalent bonds breaks due to that some of the electrons also. For example, three covalent bonds breaks. Due to that three electrons jump to the conduction band due to the break of three covalent bonds. Then three holes will be generated. Then why the remaining holes are generated here? Here in the conduction band only three electrons jumps, but in the valency band, 3 holes should be formed, but I drawn more holes. What is the reason? Write in the chat box. Write in the chat box. In conduction band, valency band, 3 electrons from valency band jump to the conduction band, then 3 free electrons generated. But in the valency band also 3 holes should be present, but I drawn many holes. What is the reason? Can you write in the chat box? Do it fast. I'm waiting for a few seconds. Nobody is giving the answer. Right. 3 electrons jumps to the conduction band. I will tell. 3 holes are generated. When how many electrons jump to the conduction band, that many holes are generated. Okay, no problem. The remaining holes generated due to the boron. And the boron are the trivalent. 3 valence electrons are there. 3 valence electrons forms the 3 covalent bonds, but the fourth bond is incomplete because boron has 3 valence electrons, but 4 bonds are there here in the diagram you see. But in that one band is incomplete. Then to complete the bond, boron also should have the fourth valence electron, four valence electrons, but it is have only 3 valence electrons. That's why one electron is less. That's due to the less of electron. Okay, so one vacancy is there. One to fulfill the fourth covalent band, that vacancy is called as the hole. Like this, the hole will be generated in the valency band. Understood? And like this, so many boron atoms we are adding, impurities we are adding, that's why so many holes are generated. That means in the p-type semiconductor, right, number of free electrons is not equal to the number of holes. Okay, number of free electrons not equal to the number of holes. I'm going to erase this. You take the screenshot. B is trivalent, boron is the trivalent. Aditi giving the reply. Okay, due to the trivalent material and the extra holes are generated, right? Okay, how many boron atoms you are adding, that many extra holes will be generated. Okay, right, very good. And next continuation, let us go for the continuation. What we are doing it here in the oh, p-type semiconductor, right? In the p-type semiconductor, which type of semiconductor we are discussing? P-type semiconductor. In the p-type semiconductor, p-type semiconductor, right? In the p-type semiconductor, in the p-type semiconductor, which are the majority charge carriers? In the p-type semiconductor, the holes are in more number and electrons are less number. That's why in the p-type semiconductor, holes are majority charge carriers. Okay. In the p-type semiconductor, holes are the majority charge carriers. That means holes are more number, right? And minority charge carriers are what? Electrons. In p-type semiconductor, holes are majority charge carriers. Majority charge carriers. And electrons are minority charge carriers. What is the meaning of this? More holes are there and less electrons are there, and electrons are minority charge carriers. That means the number of charge carriers is increased by adding impurities, right? The current will be increases. Minority charge carriers. Minority charge carriers. Okay, right. And now in this, what happening? Which density is more? Right, the hole density is more. The hole density is more than the electron density. Is it right? Hole density more than electron density. Okay, right. In this, what about the Fermi energy level? Fermi energy level what? Fermi energy level, Fermi energy level, Fermi energy level is Fermi energy level, its name is there here. The Fermi energy level, there is another name is there, that is called as acceptor level. In the p-type semiconductor, Fermi energy level is called as acceptor level. Why acceptor level? Why it is acceptor level? Because it is every boron atom, it is ready to acquire one electron. Is it right? Boron atom has only 3 valency electrons, but the germanium require 4. Is it right? The boron has only 3, 3 valency electrons, right? 3 valency electrons. Like this, one bond is empty. Okay, one bond is empty at here, and here to fulfill this bond, one vacancy is created it here. Here there is a one vacancy is for the electron. That means it is ready to accept one electron. That's why it is called as acceptor at acceptor level. And then acceptor atom is said to be, we are adding acceptor atom in the p-type semiconductor. It is ready to accept one electron, right? And acceptor atoms we will tell. And the Fermi energy level at acceptor level is near the valency band. Fermi energy level or acceptor level is near the valency band. Fermi energy level is the near the valency band. Why? Why it is near the valency band? Because you see, holes are the more number. Holes are more number. Right? Holes are the majority charge carriers. Holes are in more number. This is valency band. In the valency band, more holes are there, but in the conduction band, less electrons are there, because electrons are minority, holes are majority. Right? This is the conduction band. And now what happens at here? The Fermi energy level. Fermi energy level is the average energy level. Okay, average energy level means these holes are more number. That's why here valency band energy is more and conduction band energy is less. If you find out the average, then you will get the near to the valency band energy. That's why the Fermi energy level is very close to valency band, not at the middle. Okay, it is close to the right valency band. This is called as acceptor level. Acceptor level, right? Okay, this is about p-type semiconductors. What we discussed till now, p-type semiconductor. Okay, next let us start n-type semiconductor. There are two types of semiconductors are there, extrinsic semiconductors, and the second one is the n-type semiconductor. What is n-type semiconductor? P-type and n-type, both are the extrinsic semiconductors. What they are? They are the extrinsic semiconductors. Extrinsic means we will get them by adding impurities. And which type of impurities we have to add to form the n-type semiconductor? If pentavalent impurities, right? Pentavalent means what? 5 valence electrons. Okay, if pentavalent, fifth group elements, pentavalent impurities, if pentavalent impurities are added to pure semiconductor. Okay, if pentavalent impurities are added to pure semiconductor, if pentavalent impurities added to the pure semiconductor, then it is called as it is called as n-type semiconductor. Okay, n-type semiconductor. Clear, students? Right. Now what we have to do here? What we have to do? Pentavalent impurities we have to add. Example of pentavalent impurities. Example of pentavalent. Example of pentavalent impurities. Example is fifth group elements. Can you tell fifth group elements what are they? Can you tell? Right, phosphorus. Previously was said what I said, boron, aluminum, gallium, indium, thallium. And here I will tell the phosphorus, arsenic, antimony, okay, bismuth. These are the example for the pentavalent impurities. If this pentavalent impurity is added to the pure semiconductor, then it is called as n-type semiconductor. N-type semiconductor. Okay, I will explain clearly and you listen very carefully. And that is what we have to do here. We have to add the pentavalent impurities. Pentavalent impurities. For what we have to add pentavalent impurities? We have to add pentavalent impurities means what are the pentavalent impurities? What are the pentavalent impurities? Phosphorus. One example I will take phosphorus. It is added to what? For what we are adding? Pure semiconductor. Pure is what? Intrinsic, right? Intrinsic semiconductor. Pure semiconductor. Can you give the example for the pure semiconductor? Right. Pure semiconductor is the germanium or silicon, and it is added. And what you are getting? N-type semiconductor. We are getting. We are getting N-type semiconductor. We are getting. Is it right? P-type how you will get? P-type how you will get? This pure is called as intrinsic, and if this pure is mixed with the trivalent, that is called as P-type. And if pure is mixed with the pentavalent impurity, then that is called as N-type semiconductor. Right? Now, what are the majority charge carriers in the N-type semiconductor? What are the minority charge carriers in the N-type semiconductor? If pentavalent impurity is added to the pure semiconductor, then what happens? That we will discuss now. Right. Clear, students? Okay, good. Clear. Priya, keep learning. Be happy in the mood. Very interesting topic. बहुत मजा आएगा आपको. Right. N-type semiconductor. Then how it will work? N-type semiconductor. Let us discuss. What we have to add it here? What we have to add? We have to add the phosphorus. Right? Phosphorus is the pentavalent impurity. Means how many electrons are there? 5 valence electrons. 1, 2, 3, 4, 5. 5 valence electrons. Added to what? Pure semiconductor, germanium. Germanium is tetravalent, means 4 valence electrons. 4 valency electrons. This is the germanium. 4 valence electrons it has. This is the germanium. It has 4 valence electrons. Germanium, 4 valence electrons. Right? Very nice, very nice. Now, bonds we will draw. Right? This phosphorus has the 5 valency electrons. In that, the 4 valency electrons forms the 4 covalent bonds. Phosphorus 4 valency electrons forms the 4 covalent bonds with the 4 neighboring germanium atoms. And one electron, phosphorus has one more extra electron. This extra electron is the valency electron. It is also, it is free, it is not in the bond, it is free. Then it can act as a free electron. It can act as a free electron. It can escape from the nucleus very easily by gaining little energy. We can consider it as a free electron. That means one phosphorus atom will generate the one free electron. Like this, if you add the few phosphorus atoms, then for example, if you add the certain 1 gram of phosphorus atom, then at the moment 1 gram of phosphorus sample if you will add, that contains the lakhs of phosphorus atoms, then lakhs of free electrons generates. Lakhs of free electrons will be generated. Then this is, for example, we are adding the 10,000 phosphorus atoms. If you add the 10,000 phosphorus atoms, then 10,000 free electron will generate. 10,000 free electrons generates. Right now, 10,000 free electron generates. For example, 10 covalent bonds also breaks. 10 covalent bonds breaks. Then what happens when 10 covalent bonds breaks? How 10 covalent bonds breaks? Due to thermal energy. This is just due to impurity it is generated, this free electron. Like this 10,000 phosphorus atoms you added in 10,000 free electrons generated. But due to break of the covalent bond, why the covalent bonds breaks? Due to thermal energy or any other energy. Right? Covalent bond break means this electron will escape from the band. Right? Whenever it will escape here, vacancy is created, one more hole generated, one more electron generated. That means in the E in the when one covalent bond breaks, then one electron hole pair generates. One electron hole pair generates. Like this, 10 covalent bonds breaks means 10 electrons will produces, and 10 holes also generates. 10 electrons, 10 holes will be generated. Then total number of electrons, what happens due to the 10,000 phosphorus atoms, 10,000 free electrons, just due to the break of the covalent bonds, 10 electrons, total 10,000, 10 electrons are there. What is the total number of holes? Only 10 holes. That means which are the majority charge carriers? Right, electrons are the majority charge carriers and holes are the minority charge carriers in n-type semiconductor. Right now? Nice, na? Students, uh, only 5 viewers are there now. I want the names of the members, those who are watching. Priya Mato, Aditi, or who is watching in the live? I want names. Write in the chat box. This ellipse is not erasing. I don't know why. Okay, leave the ellipse. Okay, don't consider it. And now, next, we will write some more information, and that is how the valency and conduction band is there. This is the valency band. This is the valency band, and this is the conduction band. Right? Conduction band. So many free electrons are there. Electrons are very more number. Why electrons are more number? Because here how many phosphorus atoms added, that many electrons are generated, free electrons are generated. Because phosphorus has extra one electron because it is a pentavalent, right? More electrons are there. And why holes generated in the valency band? Because some of the covalent bonds may be break, right? Holes are the minority charge carriers, right? And what about electrons are more number? That's why electrons energy is more and the holes energy is less. If you find out the average, then you will get the energy level, and that is near to the conduction band. Okay, then this is the Fermi energy level. This is the Fermi energy level in the n-type semiconductor. This Fermi energy level name is donor level. Why it is donor? Why it is donor? Because this phosphorus atom is a donor atom. Donor atom, it is donating one electron. Is it right? That's where phosphorus atom is said to be donor atom. Then we will write the information now. What happening in n-type semiconductor? In n-type semiconductor, what are the majority charge carriers? In n-type semiconductor, which are the majority charge carriers? Electrons. Electrons are majority charge carriers. Electrons are majority charge carriers. In n-type semiconductor, there is no ellipse set here, you see. In n-type semiconductor, electrons are majority charge carriers. And holes are the minority charge carriers. Holes are minority charge carriers. Holes are minor charge carriers. Means electron density is very much more than the hole density. Okay, right. And next one is the, I'm going to erase this and you take the screenshot. I am going to continue. We write here Fermi energy level is um, if you want we can continue on. Okay, now let us see what is the location of the Fermi energy level in this. Fermi energy level. What is the name of this one? Donor level. Donor level. Where it is? Donor level. Where it is? Donor level is near the conduction band. Conduction band. Okay, right. Next one is the one small point I am going to do. Relation between the relation between the relation between Ne, NH and Ni. Okay, right. Ne means what? Electron density. Okay, electron density means electron concentration. Okay, or electron concentration means number of electrons per unit volume. Hole concentration, number of holes per unit volume. Okay, intrinsic charge carrier density. Then there is a one relation is there, one formula is there, directly you can remember, no derivation for that. Okay, that is Ni square is equal to Ne into Nh. This is the formula, very important formula. Okay, right. And what is this? What is this? Ne. Ne is the Ne is the Ne is the electron density or electron concentration. What is electron concentration? Number of electrons per unit volume. Number of electrons per unit volume. What is NH? Hole density. Hole density or hole concentration. What is the meaning of this? Number of holes per unit volume. Number of holes per unit volume. And Ni is what? Intrinsic charge carrier density. If holes and electrons are equal number, in intrinsic, Ne equal to NH equal to Ni. Ne equal to NH equal to Ni means Ni we write Ni square equal to Ni square. Intrinsic charge carrier density. Intrinsic means without impurities. Without impurities, Ni is equal to Ne equal to NH. If the impurities are not there, how many free electrons are there? That many holes are there. In intrinsic charge carrier density. Charge carrier density. Okay, right. This is the relation between the Ne and NH and Ni. Right? Okay. Is it clear, students? I am going to close, and today I will take again one more class in the evening. When not have enough time as well to complete the syllabus. I want to take. Actually, what happened? I planned to complete the total chapter in 1 hour only. I wrote everything. When I wrote everything, what happened? That is not functioning. That pen tab is not functioning. Then I deleted everything. Then after that, I am teaching while writing. I am teaching. Now it is working. Okay, right. Thank you to all. I am closing the class. I will give the time in the evening.